The year was 2003, with Halloween approaching. 93 million miles away, an angry sun began to vent its rage. Dark regions, called sunspots, appeared unexpectedly on its surface, a sign of rising tension within. It had been 3.5 years since the sun last erupted in fury, at the peak of an 11-year cycle of solar flare-ups. Back then, we got ready for it. By shutting down satellites that were vulnerable to high levels of radiation. But no one expected this. In what should have been a low point in solar activity, the sun erupted in a series of massive explosions, called coronal mass ejections, or CMEs. Electrified gas clouds, weighing billions of tons, raced outward. Solar telescopes recorded the action. The largest emission of solar X-rays ever seen. The hottest flares at tens of millions of degrees. And the fastest, reaching speeds clocked in excess of 6 million miles per hour. The sun became a giant plasma weapon, more potent than in any science fiction, and pointed right at our home planet. On Earth, the Halloween storms produced some of the most spectacular auroras ever seen at the North and South Poles. They also brought jolts of electricity that caused power outages in Sweden and disrupted airline navigation. In space, these storms damaged 28 communication satellites and destroyed 2, and they didn't stop there. As the energetic surge swept past Mars, it was so strong, it burned out the radiation monitor aboard the Mars Global Surveyor spacecraft. Ironically, this instrument was designed to study radiation that human explorers might encounter on future missions beyond Earth. Months later, the rush of solar energy washed over the 2 Voyager spacecraft on their way to the far reaches of the solar system. CMEs like these have been known to blast their way out to the far edges of the solar system, where the solar wind meets the flow of gas moving around the galaxy itself. This stormy season on the sun lasted about 5 weeks, but it was by no means the worst. A solar eruption in 1859 was so powerful it set fire to telegraph offices. Several people got nasty shocks simply because they were working with metal objects. And for the next few nights, auroras were reportedly bright enough to read by. A similar storm today could easily cause more than $2 trillion in damage to our high-tech infrastructure, 20 times greater than Hurricane Katrina. But believe it or not, the threat is about to get even worse. We are beginning to change the way we acquire and use energy by expanding our power grid to accommodate wind farms, solar energy arrays, new nuclear plants, and other renewable sources. This grid will get even larger and smarter, with microprocessors in almost every device, communicating and negotiating with one another, running everything from air conditioners to power plants. A sudden surge of solar activity could strike the grid directly, inflicting a substantial amount of damage on the emerging smart power economy. To understand what a powerful force the Sun can be, take a look at Venus. At almost exactly the same size and mass as Earth, it's truly our sister planet. The thinking is that long ago, fierce solar winds stripped off lighter water molecules from its upper atmosphere. What was left was a witch's brew of acidic gases and carbon dioxide that thickened at lower altitudes, rising to some 90 times the density of Earth's atmosphere. At a concentration of 95% in Venus' atmosphere, CO2 gas trapped increasing amounts of sunlight and drove surface temperatures close to 1,000 degrees Fahrenheit. How did our Earth avoid such a harsh fate? One of the main reasons is that our planet has what Venus lacks: a natural defense against solar attacks. Earth spins around on its axis once every 24 hours. This has an effect on molten iron welling up from deep in its core. It's kind of like the alternator in your car. These plumes of hot metal generate magnetic fields that extend beyond our atmosphere and enshroud the Earth in a protective field. Venus, on the other hand, spins so slowly that one of its days is 243 Earth days long. That's one reason it lacks a strong magnetic field. While Earth's magnetic field may be strong, it's not impenetrable. In fact, when the Sun shoots a CME in our direction, and that blast coincides with Earth's magnetic field, that chain of events is called a geomagnetic storm. Air travelers, whose routes fly near the poles, get a slightly increased dose of radiation, and the crews who fly them often need to keep track of their cumulative exposure. But space travelers are at much greater risk. Earth's atmosphere thins rapidly with increasing altitude. Outside its protective envelope, those living on space stations get twice as much radiation as the rest of us, even when the Sun is quiet. When it erupts, as it did in 2003, astronauts and cosmonauts can absorb a whole year's radiation dose in just a couple of hours. With our dependence on computers and electronic communications growing by the day, we have begun to launch a fleet of spacecraft to monitor the Sun. Some positioned in low Earth orbit, others out where our magnetic field meets the solar wind, and even beyond. Data from these satellites are revolutionizing our understanding of the Sun and helping scientists predict solar eruptions more accurately than ever before. Solar outbursts get their start deep within the core of the Sun. The Sun's immense gravity squeezes hydrogen atoms. The pressure and heat rises, causing a fusion reaction in which the hydrogen atoms crash together, merging to form heavier atoms like helium. This process gives off heat, which rises in plumes to the surface of the Sun. The SOHO spacecraft can see the result by recording ultraviolet light. It detects a wavy pattern of gas on the Sun's surface, along with a super hot halo of gas called the corona. The white regions are places where the rising gas suddenly escapes, forming loops that rise into space and fall back. There are times when this smooth sequence of generating and releasing energy gets bottled up by a magnetic field spun off by the Sun's spinning turbulent core. Using data from the Sun's exterior, scientists have modeled these fields as they erupt all around the Sun's surface. These field lines twist and loop around,